Thermodynamics and heat. Some questions to ponder. What is heat? What is the mechanical equivalent of heat? What is conduction? What is convection? And what is radiation?
Heat. Temperature. Warm, cold, warm, cold. But if I leave my hand here long enough, the countertop doesn't feel as cold as it did before. If I move my hand to a new part on a countertop, it feels colder. Move it back here, it's not as cold. So I must have transferred some of my thermal kinetic energy from my hand to the countertop. And that process is called heating.
Heat. Heat is the transfer of thermal energy from one body, substance, or system to another. Heat is kind of interesting. Heat is not thermal energy. It is the transfer of thermal energy. An object does not have heat, but it can heat another object by transferring some of its thermal energy to the other object. So that's the biggest misconception. People think that if something is hot, that it has heat. It doesn't. It has temperature. And this object has a lower temperature. And there is no heat in this system right now. They're isolated from one another thermally, and so there would be no heat. If they come in contact, the warmer object would transfer thermal kinetic energy to the cooler object, and so heat would flow. That flow of thermal energy from the hotter to the cooler is called heat. And so we would have heat going from the 80 degrees Celsius to the 10 degrees Celsius object here, and we'd have some heat. Eventually, these two objects would reach a thermal equilibrium, and when they did reach a thermal equilibrium having the same temperature, there would be no more transfer of thermal kinetic energy, and again, we would have no heat, even though the objects were in contact.
The temperature of this water is now 22.4 degrees Celsius. Can we increase the temperature of a liquid with friction? After 2 minutes of agitation, the temperature has risen very slightly to 22.6 degrees Celsius.
As you just saw in the past video, the beater raised the temperature of the water slightly as it spun around. James Prescott Joule did a very similar experiment, but he dropped weights, and these weights, as they fell, spun paddles in water and raised the temperature of that particular water. From his experiments, they created what's called a mechanical equivalent of heat, this mechanical energy transferring into this thermal energy. So from that, we get a new unit to look at here. 4.186 joules of mechanical energy is equivalent to something we call 1 calorie. 1 calorie is the energy needed to increase the temperature of 1 gram of water by 1 degree Kelvin or Celsius at standard atmospheric pressure. So if we raise 1 gram of water 1 degree Celsius or Kelvin, then we have the equivalent of 4.186 joules of energy to cause that rise in temperature. That's called a small calorie. There's also something called a large calorie, which is really just 1,000 times the small calorie, or 1 kilocalorie, and that is given a symbol capital CAL, and it's called a large calorie or food calorie or kilocalorie, and that is the energy to increase the temperature of 1 kilogram of water by 1 degree Kelvin or Celsius. Again, 1,000 small calories. This unit of a kilocalorie is important because this is too small for practical purposes on a human scale. So when you hear of food calories, which is the most common one you'll hear of, we're really talking about kilocalories of energy. So let's see how much kilocalorie really is, actually how much pound of fat is here on our bodies. So go out, pause the video, go out on the internet, open a new tab in your browser and do this search. How much energy is there in 1 pound of fat? That's a lot of energy, because remember 1 kilocalorie is over 4,000 joules, so that's a lot. In fact, I did a little calculation on my own, and a 60-watt bulb, which is a standard light bulb in your home, I think if I calculated properly, the 1 pound of fat would power a 60-watt bulb for 67 hours. It's kind of gross if you think about it. So here you have a chance to do some work with the mechanical equivalent of heat calculation here in calories. Let's say you eat a Snickers bar. It has 296 kilocalories, or food calories. How much work in joules would you need to do to burn off that Snickers bar here? And then once you've calculated that, let's pretend that you're 68 kilograms here, and you climbed up a hill, and the question is, how high would you need to climb up a hill in order to burn off that 1 Snickers bar? Go ahead and pause the video after, and then after you're done with your calculations, come on back and see how you did. So how did he do here? It's kind of alarming, really, right? So we recall that work causes a change in energy here, and so the 296 calories, the first thing is we could see how much work that was, and so 296 calories times the 4,186 joules per calorie is a total amount is 1,239,056 joules. It seems too big. It's kind of crazy. Once you came up with that amount of work, you can use that and equate that to the potential energy from climbing up a hill that you would need to do to burn off that amount of energy the Snicker bar gave you. And so finding out how high you'd have to go, we'd have to divide both sides by mg here, and wow, you'd have to climb 1,860 meters. Well, that's assuming you were 100% efficient. So this is the answer I was expecting you to get. Technically, we humans are only about 20% efficient, and so we would probably only need to climb about 372 meters. But 372 meters is still pretty darn high. So it's amazing how much energy there is in these food calories. So we've talked a little bit about heat and heating, but now we need to talk about the 3 different ways that we can heat a substance or system or object. The first to talk about here is conduction. If I had a rod here and I put it near a fire or in a fire, heat would be conducted up that rod through the molecules in the rod. So as these molecules vibrated more vigorously when they were receiving the heat from the fire, they would transfer their thermal kinetic energy by bumping into other molecules, which would bump into other molecules, and that kinetic energy would transfer up the rod here. Would transfer up the rod here, and that's called conduction. The next way we heat is through convection. By heating air molecules right above a flame here, the air gets warmer, and actually the warm air as a fluid rises. So convection is usually associated with fluids. The warm fluid rises and the cool fluid would sink, and so this air would rise and carry with it its thermal kinetic energy. And so when the air passed your hands at a higher temperature, it would transfer heat to you by carrying it vertically upward as the fluid rose. A third way we can heat objects is through radiation. Now notice your hands aren't above the fire here, so there's actually heat that comes sideways this way through electromagnetic radiation. A band of the electromagnetic spectrum, the infrared band, actually carries thermal energy. And so that's the kind of energy that we receive from the sun, for example, besides the light energy from the sun. The thermal energy, when it's hot and you're feeling the sun's heat, is thermal radiation. It's electromagnetic energy carrying heat.
We're going to use this burner to learn a little bit about the three ways we can transfer thermokinetic energy. In other words, the three ways we can heat. The first one we're going to explore is called conduction. To do that, I'm going to heat up the grill right here, and that'll be the grill will be my conducting elements here. There we go. You can see the flame here heating up the grill right here, and we'll let it heat up for just a little bit here. And so we're heating up the grill directly with the flame. Now I'm going to turn off the burner here. Here we go. So now I'll touch this and see if I can feel a conduction in my skin. Ah! Well, I just learned about conduction the hard way here. That's the direct transfer of heat through a particular substance from one molecule to the other. And it's usually a slow process, but in my case, that was a fast process. Now for the other two types of heat transfer, transfer of thermokinetic energy. Our next one is convection. Whoops. Convection, if you put your hand over the flame, over the top, a ways away like this, ooh, that's even pretty hot. I'll turn this down a little bit. And you put your hand above it a ways, you can feel the heat rising. You can kind of feel it going over you like waves of water. And that's because literally air molecules are transferring the heat. The air molecules from down here are actually rising and physically moving in a fluid up and passing my hand. So the fluid the warm fluid rises and transfers the heat through that fluid transfer process. The third way we transfer thermokinetic energy is through radiation. If I'm off to the side of the flame here, I can feel the heat from the flame over here off to the side, and that's through radiation. So the radiant heat energy from the flame and also from the molecules as they're conducting upward give off that radiant heat. That's a lot less intense. The radiant heat is a lot less intense than, turning this down a little bit, than either the the convection transfer, and a lot less, obviously, than the conduction transfer.
So, hopefully we know a little bit more about heat. What is heat? What is the mechanical equivalent of heat? What is conduction? What is convection? And what is radiation? Scratch's parting thought. And I hope you continue striving for continuous improvement.